All right. Okay. All right. So let's jump right in. Okay. So we're gonna do this example here. Okay. This is gonna be so let's just step back a moment here. So we've done variation of parameters on equations that we couldn't do method of undetermined coefficients. So this equation, the reason why we can't use method of undetermined coefficients is because you see here, it's written on in orange here. These are not constant coefficients here. So you can't use method of undetermined coefficients. You can find this homogeneous solution using Euler's equation, thinking of this as an Euler equation, using initial equation, but we've never done non-homogeneous Euler, and this is the first time we've done it, but we had to use variation of parameters for it. This one, you could, if you look at the left-hand side, they do have constant coefficients, so it looks like you can do the method of undetermined coefficients, but you can't because the right-hand side is secant of t, and that's not of the form exponential or sine or cosine or a polynomial. And in fact, the particular solution is quite complicated for this, and you would have never thought that this would be the solution form, and you had to do the variation of parameters. And we also looked at how you can do the variation of parameters quite easily by just using these formulas for V1 prime and V2 prime. These formulas were derived a couple ways. One way was to look at the system of equations and then do elimination, and this is called Cramer's rule. The other way was to just invert the matrix when you build the system, rewrite the system as a matrix equation. And these formulas naturally come out, where the Wronskian is defined as the determinant of this matrix x1, x2, x1 prime, x2 prime. They're literally just x1 and x2 copied below with the primes on them. And that determinant is the Wronskian that goes in there. And then, of course, the proposed solution that we have is built off of x1 and x2, where v1 and v2 are now are equal to these, and it's designed to satisfy the differential equation. So this equation here is more complicated. Let's say that you are given that you can't really, I can't just give you this right away and just say solve, because we don't really even know how to find the homogeneous solution for this, but I give you one. So I'm giving you that x of 1 is one of the homogeneous solutions, e to the negative t. And so you'll first do reduction of order on this, because you need to find the other homogeneous solution. Of course, this is a non-homogeneous equation, so we're going to have to do variation of parameters after that, especially since this is not a form that, you can do method of undetermined coefficients on. So you're going to do reduction of order on this. The reduction of order says that you're going to propose that your general homogeneous solution, so I'll just write this as XH. Your general homogeneous solution is going to be built off of some V times your first homogeneous solution. So that V is some function of t that we're going to find that forces this thing to satisfy the differential equation. So when you do that, you'll get your derivatives. Your derivative x prime is going to equal v prime e to the negative t minus v e to the negative t. That's just the product rule, assuming that v is a function of t. And then the second derivative is going to equal v double prime e to the negative t. And then you'll have two of these when you combine a couple terms in the product rule, plus the last term, v e to the negative t. This is because you take the derivative, chain rule, and the negatives. So that's your second derivative, and then you're just going to plug this in. So you're going to take the second derivative, which is, well, there's all this stuff. So this is 2t, 2t times, you're going to copy this thing, It's the second derivative, times plus 4t plus 1 times, you're going to paste in the first derivative, plus 2t plus 1 times x, x is actually v e to the t, e to the negative t. And this is supposed to equal 0. Okay, right off the bat, you can cancel all the e to the negative t's because you can just divide everything by e to the negative t, and you'll notice that every single term has e to the negative t in it. So just say we divide all that out. All right, once you divide all that out, you have just the 2t times v double prime minus 2v prime plus v, plus you'll have the 4t plus 1 times the v prime minus v, plus 2t plus 1 v is equal to 0. I'm going to underline all the v terms. This is a v term. This is a v term. This is a v term. I'm just going to underline this whole thing. Okay, so if you look at this, you'll see that you have 2t plus 1v. This is going to be a 2tv. This is going to be a negative 4t v and a negative v. So this will be minus 4t. This is a plus 2t. This is a plus 2t. So those are going to be 4t minus negative 4t. And then there's going to be a minus v, but there's a plus v. So if you actually distribute all these out, you'll see that these v's will cancel. All these v terms will cancel. That's always going to happen for whenever you have reduction of order, your v terms will cancel. And you can confirm by distributing that you'll get a negative 4t v, but there's a plus 2t and a plus 2t. You have a minus v and you have a plus v. So those are going to cancel. So now you're left with 2t v double prime. I'm just going to combine. So this one's right here, 2t times minus 2t minus 2v prime. This is going to be a 4t plus 1v prime. So you have, let's see, 2t times minus 2v prime is negative 4t v prime. This is a positive 4t v prime, so there's only one v prime left. It's equal to 0. Okay. Then, in general, you can let w equal v prime to reduce the order of this equation. So you get 2t w prime plus w is equal to 0. And you can do separation of variables. So you say 2 dw over dt is equal to negative w over t. I just rewrote this as dt, by the way. I wrote this as this. I moved this over, so it became negative and divided by t. And then there's just one more step to separate this. So I'm just going to do 2 dw divided by w is equal to negative dt over t. Now you can integrate. You'll get 2 ln of absolute value of w is equal to negative ln of t. I'm using t is greater than 0, so we're going to drop the absolute value on that. Plus, there's a constant on both sides that we can consolidate as c1 on the right. You can divide both sides by 2, so you get ln of absolute value of w is equal to negative half ln of t, plus c1 divided by 2 is another arbitrary constant, so I'm just going to say that's c1. And then I'm going to take the exponential of both sides. The absolute value of w is equal to, and then also when I take the exponential as well as I'm going to pull this exponent up because then I can cancel the exponential and the log. So it's going to end up becoming And then, of course, there's a splitting of the exponential. So the e to the c1, e to the ln. Just move this down. This whole thing. Ln of t to the negative 1/2. And you can drop the absolute value. So you'll say w is plus or minus e to the c1. E and the ln's cancel, so this will just be t to the negative 1/2. But then I'm going to redefine this as a new constant c1. This is just an arbitrary constant anyways. Okay, so what does this mean? So what is w? W is v prime. So v prime is equal to c1 t to the negative 1/2. We integrate this. To get v. And that gives you that it's going to be, the integral of this is 2c1 e to the, not e, t to the 1/2. And I'm going to read plus c2. There's another integration constant. And then I'm going to redefine this as a new c1. So that leaves us with our v is equal to c1 square root of t plus c2. Just t to the 1/2 is square root. Therefore, our homogeneous solution is equal to this formula, ve to the negative t, but with this v that we just found. So it's going to equal, copy this. This is my v. Times the e to the negative t. So this is our homogeneous solution. Given that one of the homogeneous solutions is given to us as, what is it, e to the negative t, we can always find the full homogeneous solution inclusive of the second homogeneous solution. So it's like, yeah, you can, let's multiply it out. So we'll just say this is the same as c1 square root of t, or maybe I'll just write it this order, c1 e to the negative t square root of t plus c2 e to the negative t. Okay, so those are your two homogeneous solutions. I would say this one was the, I mean, it doesn't matter which one we label as which, but I'll just label this one as x1 and this one is, well, what do we have? x1 is e to the negative. Okay, we'll just flip it around. It doesn't matter which one you label as which, but this is like our other homogeneous solution. All right, so this is the homogeneous solution. This is a non-homogeneous equation. We're going to have to use variation of parameters because this doesn't fall under any other method that you can use. They're non-constant coefficient plus a very exotic right-hand side that doesn't fall under method of undefined coefficient. So what do? We need both the homogeneous solutions to be able to construct the variation of parameters. You need x1 and x2. You got e to the negative t square root of t. You need their derivatives. So x1 prime is equal to negative e to the negative t. x2 prime is equal to negative e to the negative t square root of t. This you got to do the product rule. So you're going to have plus 1/2 times e to the negative t to the negative 1/2. Okay, those are your homogeneous solutions and their derivatives. This over here. And then just to condense this, I'm going to think of this as my matrix. So the Wronskian is just the determinant of this. So it's going to become this times this, which is negative e to the negative t times, no, actually, it's just going to be e to the negative t times all of this. So I'm just copy this. So do this, close this up, make this all purple. And then this is going to be minus by this, but there's a minus here. So it's going to be minus of a minus. So it'll be plus E. There's a minus t, so they'll combine to negative 2t. And then square root of t. All right. Now, if you distribute this e to the negative t and this negative e to the negative t times this, that's just a negative version of this. So these will cancel. And so you're left with just 1 over, there's a 2 because there's a half. You have these two on the bottom, so I would say e to the 2t, and then square root of t. That's your Wronskian. Okay. Now we have formulas for, I'm just going to copy those. These formulas for v1 prime, v2 prime. Using the Wronskian, so we'll just take those, paste it in. All right. Now we're going to have to find the correct f. The correct f for when we derived these formulas for v1 prime, v2 prime using the Cramer's rule was looking at this equation with this divided out. So this 2t has to have been divided out. So there's only a 1 in front of this. So that means that your f is actually going to equal 3 over the, there's a 2 because of the 2t here. And then I'll just write it like this, e to the t square root of t. So that's your actual f. Okay, so now let's use this. We're going to say my v1 prime is going to equal the negative of, I'll just write everything else. So it's going to be negative of 3 times my f is, so this is where all my f is coming. So it's going to be all of this 2 et t square root of t. W is the Wronskian. It's down here, but it's divided. So I'm going to put that on the top, but I'll also put the x2. So x2 is actually this thing right here. So I'll just write this as to the negative t square root of t. So we've got the negative, and then we have the 3. We have all of this. You have the x2, which for our case is this. And then we're going to have to multiply by the Wronskian, which is going to be times 2 e to the 2t square root of t. This is on the top now because, it's dividing. So I make this a little bit longer. And maybe I'll make colors for this. So technically, this is your f, right? Yes. It's from this 2 right here. We divided 2t. This 3 e to the t square root of t has to be divided by this 2t because all these formulas we got, we assumed that we're starting off with this equation right here where there's not anything in front of the x double prime. And you can always, and that f is for the case where this is already a 1 here. And so if you ever have something in front of here, you can always make it into this form to get the correct f, really. We don't really care about pt, and q of t never shows up later. But to get that correct f, you can always write it in this form by just taking whatever's in front of this and dividing it out. Because all these formulas assumed that that was the form we started with. So that's where that f is coming from. So this blue stuff is copied here because that's my f. There's a negative in the front. X2 is this. We chose that to be our second homogeneous solution. The Wronskian is this, but if you're dividing, then it goes on the top. Okay. And so let's do the same thing kind of with the other one. The other one is going to equal, there's no negative, but it's going to have kind of the same. I'm just going to copy it. It's just slight changes to it. So it's going to be like this. There's no negative in the front, but the x1 is e to the negative t. So this drops out and we just have this. But the f is the same and the Wronskian is the same. So that's going to be the case there. All right. So we're going to notice that a lot of things cancel. You can see here that if you took the e to the 2t, multiplied it with e to the negative t, that would be just e to the t, but there's an e to the t in the bottom, so all these will go away. There's a 2 here that will cancel with this 2. I guess you can at least say this square root of t and this square root of t will cancel. Yeah, so that's it. And so after all of that, you're just going to have -3 over, there's a square root of t here, but there's a full t here, so that's square root of t on the bottom. Okay, and then let's just integrate this. If you integrate this, you'll end up getting that your v1 is equal to -6 square root of t plus c1. Because if you took this is the t to the half, pull it down, becomes -3, and then goes to -2. So that's good. And then this one, the e to the 2t times e to the negative t becomes e to the positive t, but there's 1 on the bottom, just like before. 2's cancel, the square roots cancel. So you just have 3 over. This one had a square root of t up here. This one doesn't, so it's just a full t on the bottom. Then you can just integrate this. So your v2 is equal to 3 times ln of t plus c2. And absolute value can be dropped from your just seeing t is greater than 0. So those are your v1 and v2. Therefore, your full solution is going to be x of t is built off of v1 times x1 plus v2 times x2. And our v1 is this. X1 is e to the negative t. And then our v2 is this. And the v2 was e to the x2 was e to the negative t square root t. Okay, so that's your solution. And if you want to split the particular solution and all that, you can I'll write an intermediate step later, but the algebra will end up eventually giving you that this splits if you multiply it out and extract the real and imaginary, not the real, the particular and homogeneous solutions, you'll get that it would be equal to this plus, I'll just copy I'll just do it down. C1 e to the negative t plus C2 e to the negative t squared of t. Okay, so this is fine, up here is fine, but if you were interested in extracting what the real and imaginary, not the real, why am I saying that? The particular and homogeneous solution, then this is your particular solution, and this would be your homogeneous solution if you just like expanded this out. So the particular solution is, the homogeneous solution is we got that from reduction of order. This particular solution is what we were after, trying to solve this non-homogeneous equation using variation of parameters. And this is a solution form that you probably would not have expected, seeing that this right-hand side is 3 over e to the t square root of t. There's e to the negative t, and then there's square root of t just happened to go on the top instead. There's 3 somehow still remains, but then there's this extra factor of ln of t that somehow shows up. And you wouldn't be able to predict that ahead of time. So you just have to be faithful to the process, and you'll get this particular solution. All right. So that's like a big example that combines reduction of order with variation of parameters because this is a sufficiently difficult equation that requires both of those to solve the homogeneous first and then solve the particular solution. The requirement is that at least one of the homogeneous solution has to be given to you because it would be hard for you to see that x1 equals e to the negative t is a homogeneous solution to this. But once you have one homogeneous solution, you now have enough techniques to be able to solve any second order non-constant coefficient linear differential equation with any kind of right-hand side. So you just go through that process. Let's say we take the same equation, but our right-hand side is now a little bit different, like ln of t e to the t. So the x1 is still negative e to the t. Our other homogeneous solution is e to the negative t squared of t. That's because the homogeneous solution is still going to be the same because this is the same left-hand side. So I just trust me that the left-hand side is still the same. It's just the right-hand side is different. But let's use instead, using the homogeneous solutions computed in the previous problem, which is this, find the Green's function and use it to solve the differential equation. Now we have a different forcing function. So what was the whole point of the Green's function? The Green's function said that, in general, if you just had some general f of t, x of t, x2, w of 2, you integrate, but let's say you don't know, if I just kept them general, then you just can leave it as a definite integral using fundamental theorem. Say you just take the integral from initial t to some other t plus integration constant, and you write out this solution. This piece in here is the Green's function. And then we said that basically this is like a weighting function that gets multiplied to the forcing, and it tries to weight the contribution to the solution at t due to the forcing at all preceding times, so from t0 to the current time. And so the advantage was that if you know the Green's function for your differential equation, in more technical terms, it would be a Green's function for the differential operator. Then you just, and let's say you have the same equation, but the forcing changes. All you do is you just change f of s, but this whole solution form still stays the same. So we're going to compute the Green's function, just copy and paste that. So this is the Green's function equation. So the Green's function is t comma s is equal to this. So for our particular problem, our x1 is e to the negative t. Our well, we're going to have to use the correct. So this is x1 at s, so e to the negative s. And then it's going to be multiplied by x2t. So we're just going to leave that as e to the t, square root of t, minus x1t, so e to the negative t, x2s, so it's going to be e to the negative s square root of s, all over the Wronskian. Just copy and paste the Wronskian because it's the same as this here. So given the x1 and x2 we had before, this was the Wronskian. But this Green's function is saying find ws, so all the t's are s's. So I'll just say s squared s, okay? So you can check on your own using algebra. So basically you have e to the negative t is common between these two. E, the 2s comes out, there's a 2s. And so it does simplify to e to the s minus t square root of s. And then you have let me check here. If this, let's just do it. So we have e to the negative s2, so there's going to be a 2 on the top for sure. And then you're going to have e to the negative s and e to the negative s. Those are common, so I'm just going to pull e to the negative s, e to the negative t. Those are common. Then you're gonna have, so you got e to the negative s, e to the negative t, e to the negative t. Those are common. And then we're gonna take that and then just take square root of t minus square root of s. And then this is multiplied by e to the 2s square root of s. All right, that's good. And then you'll have 2e, you have 2s minus s, so it's just one positive s minus a t. I'm just combining those. And then you'll have square root of t minus square root of s. Okay, this is your Green's function. All right, so what does it say? Let's compute this integral. There's an integral up here. So let's just compute this integral right here. So I'll copy this part, and then you just tack on this other part. So we're just going to take this. I'll just take the whole thing. So this is going to be the solution. So we're going to take this. Right. Just so that there's not a lot of clutter, I'm just going to compute this integral, which is the Green's function. So basically, this goes in here. Okay, just drop this. Okay, so the only thing that's changing is this f of s. This f of s is equal to, well, we got to be careful what the f of s in this problem is. So the f in this problem is going to be ln of t over 2t e to the t. Because you're just dividing by this 2t. So this is my f. And so all that you're doing is you're getting that this integral from t naught to t of this Green's function, which you just computed, multiplied by this f. Okay, the 2's cancel. And that's all that cancels. And so you can pull out. This is an integral in ds. Okay, so there's this ds here. So I'm going to pull out let's see. All right, so this f of s, I got to be careful because these are all actually going to be s's now because we're saying the function, the function f, this is f of t, but they're saying use f of s. So that means it's going to be s, come on, 2s, e to the s, ln of s. Okay, so there's an e to the negative t that we can pull out because that's not going to be affected by this integral. So I'm just going to say e to the negative t can come out. You'll have the integral from t naught to t of, this is going to be, I forgot to put a, sorry, so I forgot to put a square root of s. This square root of s here, it should have still been here. So that means that I do have a factor of square root of s. Let's just go to a new line. So we have e to the, okay, and the other thing you can do is we can cancel this e to the s with one of this e to the s up here. So then we don't even have that anymore. So we have just s to the 1/2. I'm just writing it that way for the square root of s. It's to the, well, actually it's s to the negative 1/2 because there's an s down here. So there's a s, the square root of s up here, but there's a full s down there. So it's s to the negative 1/2. And then ln of s, and then you have that ln of s, but then you still have this factor, so square root of t minus square root of s. And you can just take the integral of this. So let's well, we could split this up. So we'll just say this is e to the negative t. And then we have your first one is going to be, I'm going to pull out the square root of t. So you'll have t naught to t of s to the negative 1/2 times ln of s ds. And then you have minus this other one is going to be the integral of, so when I distribute this s to the negative 1/2 and then this s to the square root, that combines to just becoming 1 because this is a positive 1/2 and this is a negative 1/2. So it really is just ln of s that's left. ds t naught to t. Okay. And then you're going to take the integral of these. So I'm going to spare us from, you have to do integration by parts. So this integral requires integration part. This also requires integration by parts. And so I'm just going to write the result. If you do that, it's going to become 2 square root of t ln of t minus 4 square root of t plus f1 of t naught. f1 of t naught is just some function. And it's a little bit, it's more complicated than just, it's some function that I'm just labeling as f1 because it's just going to be like when you take the definite integral, you're going to take the antiderivative of this and plug in the t in it, and then you're going to plug in the t naught in it. But it really does, it's just going to be a number in the end, and it's not going to matter. So I'm just going to leave it as just a number, and I'm going to label it as f1. And then we have that is the first one. And then this integral right here is going to equal t ln of t minus t plus f2 at t naught. I'll just underline this and show you this. This is actually going to be equal to this. And this will be equal to this right here. And so we're done. So therefore, our x of t will end up becoming, so we have this formula up here. So I'll just go back up to the Green's functions right here. So this is, I'll just take this whole thing, and that's exactly what we're going to use to construct our solution now that we found this. The hard part was finding this integral. So I'll go down a page. So therefore, we have our full solution, x of t. It's equal to all of this. And, after all that, we found that this is equal to, so I'm going to say this is e to the negative t times the 2 times the square root of, so the 2 times the square root of t times square root of t, those square roots will become just t, ln of t. Then you have minus 4t. And then I'm going to skip this term, but put it in later. This one's right here is going to be negative t ln of t. This is going to be plus t. Okay. All right. So then there's still this f1 term right here. But keep it, so I'll just write that. So there's still the f1 t naught e to the negative t square root of t. There is the minus, this f2 is going to be multiplied this e to the negative t. So it's going to be f2 t naught e to the negative t. And then there's all this other stuff. It's going to be c1. I'll just copy and paste the rest of those. This over plus all of this. But then the punchline is that you can just combine. This is just some antiderivative computed at some point. So this is just a number. I'll just say that this is just a number. And so is this just a number. So we just have the first part, which is this. Actually, I'm going to simplify it a little bit more here. So you have 2t, t minus t ln of t. So it's just t ln of t. This is a -4. This is a -1. So the +1, so this is 3t. So this combines to this. And now I'm going to say this right here, though, this e to the negative t, and then this is x1. And this is x2, right? I believe we said this is x1 and this is x2. So you can just say this is just equal to c1 plus f1t naught times your x. Well, I guess it's c2. I don't know, it just kind of flipped around. So I'll just do this plus c1 minus f2 t naught. And this is x1. But you can redefine these constants because these are just numbers. These f functions are just the antiderivative of those integrands evaluated at the initial time. So you could label this a C2 and this is a C1. And so your full solution is going to equal this. Plus, I'll write the C1 first, so it'll be C1. It's just going to be this. So I'll just copy. Well, we already know what x1 is. x1 is e to the negative t. Plus c2, x2 is e to the negative t square root of t. So this is the solution. We have the same homogeneous solution. And then this is our particular solution. But we found the particular solution by constructing the Green's theorem and then Green's function, and then taking this integral right here, multiplied by the right-hand side changed. So because of this being the new right-hand side, we divide by the leading coefficient, and then we get a new f that goes into this, and then the Green's function has the nice property that you just take this integral multiplied by this forcing, and it's quite a bit of just calculus, but you'll end up getting your particular solution. So for this one, your right-hand side is ln of t over e of t. The particular solution is like this. I mean, with variation of parameters, it's really potentially quite complicated. It's not clear exactly what you're going to get, but you just have to go through this entire process. So compared to the method of undetermined coefficients, you really have no way to predict what it's going to look like. And you just have to go through and do all this work to get it. So that's just to illustrate the fact that if you have the same differential equation, but some other right-hand side, you can, so this Green's function, once you've computed it, now you can just have all kinds of different things on the right-hand side, and it's really just this integral that you're just computing. So it's mostly a lot of just integration. But the concept is that where does this Green function come from? It comes from the variation of parameters. And then once you know that, then it's just it's a exercise in calculus to compute the integrals. And honestly, these kinds of things make me nervous trying to do it because it's like really too early. Well, it's not early, but it's my brain is kind of trying to process this. But this I think is correct, so I can double check later to make sure that this. But you see the process. Okay, so that's it for variation of parameters. We're going to step back into like 2.1 just because there's some theory that I had skipped in the past. And I wanted to revisit like why are the homogeneous solutions we got good. And we don't have a lot of time, so all I'll just do is set up the actual statement here. So consider second order homogeneous equation, general homogeneous equation like this with some initial condition, these two initial conditions. So I'll just underline them as this initial condition here, and then you have this initial condition here on the derivative. And the question is saying that show that the Wronskian at the initial time must be non-zero to be able to successfully solve for the C1 and C2 for the general solution C1 x1 plus C2 x2 to solve the initial value problem. So let's just write the initial conditions. So, okay, so you say that T naught is equal to X naught. That's one of the initial conditions. And then the other initial condition is equal to V naught. They like to use V naught because I guess, it's like a velocity because it's a derivative. Those are the two conditions. So if you have a solution x of t plus c1, x1 plus c2, x2, and you're found x1 and x2 to be two homogeneous solutions, then what do? You just plug in these initial conditions. So basically, you're going to say, what does it mean for x t naught? It just means it's going to c1, x1 at t naught plus c2, x2 at c naught, t naught has to equal x naught. Okay, that's the orange condition. The other condition is its derivative. So that means that I just have to take the derivative of this. The derivative of this is really easy. It's just c1 x1 prime, but then we want to plug in t naught into it. c2 x2 prime, we want to plug in t naught into it. And this has to equal v naught. Okay. And we want to check, we're going to try to solve this, right? So this is very general because in a real problem, you would have found x1 and x2, and then you're trying to find your c1 and c2. But I'm just leaving x1 and x2 general, and then just saying hypothetically you have these two initial conditions. There are certain conditions we must have between x1 and x2 and their derivatives so that it's even possible for us to find c1 and c2. And so we'll try to solve this and then discover that there's some condition on x1 and x2 that needs to be true. In particular, their Wronskian needs to be non-zero. And then we'll move on from that and show that that actually is equivalent to showing that x1 and x2 have to be linearly independent, means that they are basis vectors that span the space of all solutions for the second order equation. This is a two-dimensional space. So that's the main thing. And then we'll move on to systems of linear differential equations. Okay, I'll see you guys later.